Everyone. I'm going to go ahead and call us to order here. Our very first virtual E&E of the semester, of ever, really. So very exciting. Hopefully this all goes smoothly. Hannah's been nice enough to be our guinea pig here. So if something goes wrong, it's not her fault. I'll just go ahead and say that. I'm Charles Sims. I'm the director here of the Energy and Environment Program at the Baker Center. If you've been to these before, you know what you're getting yourself into. This is a bit of a kind of interdisciplinary mishmash of different perspectives on energy and environmental topics. It's kind of what we've been trying to do here from day one is get people into the same room who have different disciplinary perspectives, different ways of thinking about environmental issues, and fostering some sort of dialogue and conversation between these groups. We don't get a lot of opportunities to do that here on campus, and it's very easy to stay in our disciplinary silos. And so this is one of the few opportunities that we get to really kind of talk with one another across departments and across buildings. And so we're excited we've been able to keep this going even here within the midst of our pandemic. We've got a few things out. I'm thrilled to see that we've got 58 people who have signed on so far. That's fantastic. One thing that we'll do here before I forget, we're going to run the question and answers through the chat room. So if anyone has a question, they can just type it into the chat room, and then I will be happy to kind of forward that on to Hannah. Once you get this many people, it's sort of a bit of a mess when everyone's trying to unmute and ask questions at the same time, and you're not really sure who's talking and whatnot. So just type them into the chat room there. You can either, it's probably easiest to send them to everyone so that everyone can read the questions, and then I'll relay them as they come up to Hannah. So to get started, I want to say this is not the only talk we have for the semester. We have 4 others. On September 17th, we'll have Andrew Hoffman. Andrew is from the University of Michigan. He is in the Ross School of Business and the School of Environment and Sustainability. And he's going to be talking about how culture shapes our debate around climate change. On September 24th, we have Christoph Nolte, who's from Boston University. He's in the Department of Earth and the Environment. He is going to be talking about how to use satellite data to improve conservation outcomes and to measure the effect of conservation outcomes. November 5th, we have Rob Johnston. Dr. Johnston's from Clark University. He's an environmental economist. He's going to be talking a bit about doing valuation of ecosystem services. And then on November 12th, we have Tara Conkling, and Tara's from the Forest and Rangeland Ecosystem Science Center at USGS. So all those talks will follow the same format that you see today. We'll have them online. We'll be sending out Zoom links. So just look for those links and save those along the way. I can't think if I'm forgetting anything. With that, I'll just say thank you to Hannah for agreeing to do this, and I'll hand it over to Derek Alderman to introduce Hannah.
Thank you, Charles, for that invitation to be part of this, and I'm very honored and pleased to be able to introduce Hannah Herrero, who joined our department last year as an assistant professor of geography after completing a series of degrees from the University of Florida. And we've tried to forgive her for being a Gator, but it's something hard to get beyond, but nevertheless, we're working through it. Zoom is a pretty much humorless technology, so I think I'm probably killing it out there, but it's probably, I can't tell it. No, in all seriousness, Hannah has been an energizing and talented addition to our geospatial program, our human environment studies, our student-centered mission. She's already developed new curriculum. She's already mobilized students on projects and is publishing with them. And we really just could not ask for a better colleague in the Department of Geography. In her case, she specializes obviously in remote sensing, which is one of the things that attracted us in the Department of Geography to her work. But also what's very important is that she applies those methods and a lot of other geospatial and social scientific methods to looking at conservation, land change, landscape change, vegetation dynamics, and really very much in the context of the continent of Africa and African southern savannas, which was an area of expertise that we really didn't have necessarily in the Department of Geography until she got here. She's already been immensely prolific and productive in her time at the University of Tennessee, already has 12 very well-respected papers and book chapters to her credit, and she just recently completed applying for, and we have our fingers crossed, we'll get a NASA Early Career Investigator Award. She really is just, I think, one of the more outstanding hires that the University of Tennessee has made. No one came to hear me speak, so I'll turn this over to Hannah. And Hannah, welcome.
Thank you so much for that introduction, Derek. You're very kind. All right, let me try to share my screen for everyone. Okay, can everyone see that? Hopefully, PowerPoint. Okay, good to go. Great. Okay, so the work that I'm going to be presenting today, the majority of it is going to be an extension of my dissertation work. And then at the end, I will talk a little bit more about what Dr. Alderman mentioned with that NASA proposal that I've just put in. So today, sensors and scales in Southern Africa, an analysis of vegetation health, protection, and parks. I always try to use the return button and it never lets me. Here we go. So a little bit more about my work. As was mentioned, it's definitely focused in drylands, specifically savannas. And for the last decade, I've been working across Southern Africa. The reason that our dryland ecosystems are so important, including our savannas, they cover more landmass than any other type of ecosystem on Earth. It's over 20%. So they cover a lot of ground. They therefore support a lot of human population, a high amount of biodiversity, and net primary productivity and contribution to the global carbon cycle. However, we know that these are really vulnerable regions, not only because they're oftentimes in disequilibrium and shifting, and we'll talk about that in a second, but also because of the threats of global climate change, namely lower available soil moisture through decreases in precipitation or increases in precipitation variability that we'll talk about today, and then also because of increasing temperature, which has been unequal in much of sub-Saharan Africa. In addition to that, vegetation degradation has also been a concern across this region since the early 60s. And so degradation can be defined a lot of different ways, but in particular, what we're concerned with are things such as bush encroachment, which can be as a result of changing drivers here, as well as a total loss of vegetation. So the important drivers in savannas are going to be, first of all, right, we're talking about drylands. So definitely going to be climate is really, really important. This is a very water limited system. So water tends to generally be the most critical variable, at least up into a certain threshold. Fire is also very important in this system. When you think a lot of times about wildfires, it's seen as a negative thing, but actually there are some ecosystems that are fire dependent, and savannas are one of them. So it needs fire to help control that competition between grasses and trees. And I guess I should have started with that. What is a savanna? That's a great question, and it's definitely keeping me in a job because there's a lot of debate about what it is exactly. Is it just a transition zone between pure grasslands or more arid landscapes and forests? I don't like to think of it that way because I think savannas are really special and they deserve their own distinction, but there's some mix of grass and trees. But of course we have things like grass-dominated systems, bush-dominated savannas, and tree-dominated savannas. So one of the biggest challenges is trying to use remote sensing technology to delineate where those thresholds are between our grass, our shrub, and our tree. And this is even more complicated when we're using remote sensing technologies, because oftentimes really the only difference between our bush and our tree is going to be a matter of height rather than species. So there's that spectral signature confusion that occurs with our woody vegetation types in the system as well. So oftentimes field work is really critical. always in remote sensing, but especially in savannas and trying to delineate where those boundaries, those thresholds are. Another really important driver on this landscape are going to be our herbivores, and in particular, our large herbivores, the ones who are mass consumers. So increasing number of herbivores can sometimes lead to our degradation, our bush encroachment, which you can see here in this top right-hand picture. This is a really idyllic savanna down here at the bottom. But this bush encroachment, because of overgrazing, compacting of soil, and also depositing of point source over nutrients, excess nutrients, which is some of the problems with cattle in these systems as well. But here we're trying to focus more on the wildlife. And then humans, of course, always a big driver in everything, both at a local level in terms of resource use, if we're talking about going in and collecting bush wood for our fires, for our cooking fuel, or if we're talking about extraction of animals for nutrients, for food. And then at the broader scale, what humans are contributing to climate change in terms of increasing greenhouse gases and everything else that in turn are having a major effect on our dryland ecosystems. So the majority of my work is focused around these protected areas. So protected areas can be defined in a variety of ways. There's a lot of different categories of protected areas, from private game reserves all the way up to national parks. But for the sake of standardizing the definition, my studies today that we're going to talk about are just going to be focused on our national parks. And they really are the ecological and socioeconomic engines of Southern Africa. With increasing human population, there's increasing pressure on the landscape and landscape utilization that are limiting wildlife to smaller and smaller areas. So these protected areas are really critical in preserving biodiversity, but then going a step beyond that, they're also less dynamic on the landscape. There's a lot more activity happening outside of parks. There's a lot more changes that are happening. So trying to keep that stability inside of parks is really important for wildlife as well. The other thing to manage for here now, when we start talking about socioeconomics, are that these parks are extremely important in socioeconomic development of Southern Africa. So a lot of countries have moved away from a livestock-based economy into more of the bio-experience wildlife economy. So that's having a value that is much higher on wildlife, which then in turn gives greater incentive for people to want to conserve those landscapes. This includes bringing in a lot more jobs, things like being guides, being scouts, being wildlife rangers. But when there's actual value on the wildlife, then that gives people a reason to want to conserve. So these protected areas are really important on the landscape. But as I said, there's increasing pressure from the outside. So here on our right-hand side, we have all of the, again, national park designations across 8 countries in Southern Africa. Lesotho and Swaziland, Eswatini, currently their parks are too small for the scale of remote sensing, so I've chosen to omit them from this analysis, but all other countries of Southern Africa are represented here. I'd also like to point out here on this map that anything that is outlined in red that you can see is considered a transfrontier conservation area. And so basically this is some conservation area which falls on multiple sides of some geopolitical border that are then working together, generally through a third party, to try and successfully manage these parks, protected areas, to make it mutually beneficial for both. So one example is Peace Parks Foundation, which is based out of Stellenbosch, just here north of Cape Town. And they're responsible for a lot of the transfrontier conservation logistics across Africa. But one sort of stark example that I will give you is here in Eastern South Africa / Southwestern Mozambique. We have Kruger National Park on the South African side. And that is if If any of you are familiar with Kruger, a very well-studied, maybe overly studied at this point, national park that is very carefully managed. And then on the other side of the border here, we have Limpopo National Park in Mozambique, and the exact opposite situation has happened there, where there's not a lot of management, a lot of natural resources have been depleted, and so over the years, and so coming together to make this transfrontier conservation area has been particularly important across borders where there's distinct differences in management types, and in this case, socioeconomics. Mozambican parks, which in the second part of this talk, we're going to talk specifically about this park right here, Gorongosa National Park. But in Mozambique, because the socioeconomic conditions are significantly worse than in South Africa, you can see a result of that coming out in the health of their parks. So, research questions to address here. How can we better understand drivers of vegetation health in and around national parks? How has savanna vegetation persisted in and around national parks of Southern Africa during the 21st century? And how specifically do parks compare to our buffer zones, the areas outside, which we know are really important, as their name suggests, they're buffer zones, to try to help if some sort of pressure or activity is going to happen, hopefully it happens there and doesn't actually make it all the way into the park. And this is a picture here of South Luangwa National Park, which is just here in eastern Zambia. It's a big acacia. So what specifically is a study area? How do we break it down? Sorry about all those email dinging, as I don't know how to turn that off. I got all of this data from the World Database on Protected Areas. Have a total, as I mentioned with the 2 exceptions, of 79 national parks across these 8 countries. Our small parks, we have a sample of 41 of them, a mean area of about 300 square kilometers, and a buffer zone of 10 kilometers. Our medium parks category is about 30 parks with a mean area of about 4,800 square kilometers and a buffer zone of 20 kilometers. And then for large parks, you can see the great difference. We only have 8 of these with a mean area of 23,000 square kilometers and a buffer zone of 30K. So the buffer zone size is generally chosen based on the work of Ruth de Vries back in the 2000s, should be about 3 times the size of your park. Now, of course, we're working across a range of sizes here, so that is how that number came about, for those of you wondering. But this is just to show you distribution of area and what it looks like. So the large is significantly larger. So a bit on methods, I'll do some explaining here of our normalized difference vegetation index, just because I'm not sure everyone's familiarity. So this is coming from a MODIS satellite sensor here, our moderate resolution imaging spectroradiometer, which is at 250 meters of spatial resolution. And this data was collected from March 2000 through November of 2016. This is at a 16-day resolution. And it was at a per pixel basis, atmospherically corrected, and also masked for anything like clouds, heavy aerosols, anything that was going to degrade the data. So it's all been QA, QC checked. So this monthly data, we aggregated up to the month, was compiled from this biweekly using a maximum value composite. So wherever our highest number was. So what is NDVI? So when we're talking about remote sensing, satellite imagery, each of the sensors on our satellite are going to be collecting data during a different portion of the electromagnetic spectrum. And so we can only see, right, in our red, our green, and our blue wavelengths, but satellite sensors can see outside of that, which is pretty cool because we see, right, when we're looking outside, vegetation for the most part looks green to us. Our leaves look green, right? So you might say, well, then it must be most highly reflective in green. But actually, when we can see outside of what we can see with our regular eyes, we'll notice that our vegetation is actually most highly reflective in our near infrared wavelength. So just a little bit beyond our red that we can normally see. So it is it's most absorptive in the red portion of the electromagnetic spectrum. So when we put those two bands together, we can actually get an index of vegetation health. So that's what's here on the right-hand side. We have our equation for our NDVI. It's our near infrared band minus our red band divided by our near infrared plus our red band to end up with this value that goes between -1 and +1, with values closer to +1 indicating greener vegetation, more vegetation abundance, healthier vegetation, and the closer that we get to 0, less vegetation, less healthy vegetation, and then below that into things like water, ice, rock, etc. So we collect this NDVI data from these satellites, and then we aggregated it into seasons. So most of the work that we do in Southern Africa is very seasonally dependent because, as I said, we're talking about a very water limited system. So here I have our aggregated seasons with our December, January, February being our arboreal winter, right, in the north, / the wet season in Southern Africa, as well as the second half of the wet season, our March, April, May, which is our boreal spring, Southern African wet season, second part. And then June, July, August, our boreal summer / the beginning of the dry season in Southern Africa. And then our September, October, November, our boreal autumn, which is the second half of the dry season in Southern Africa. Went one step further then to try to aggregate this so we could compare across time periods to see were there any differences across these years in Southern Africa in terms of vegetation health. So we have this grouped by season, so the seasons we just discussed, and then into 2000, 2004, 2005 to 8, 09 to 12, and 13 to 16. Now in the second part of the paper, or I'm sorry, the second part of the talk that we're gonna refer to, the first half is gonna be a pre-management baseline, and the second half is gonna be a post-management comparison. But we don't need to worry about that right now. So for this first paper that we're discussing, talking about parks and how can we understand what are the major drivers in parks for vegetation health as seen through NDVI. We have different variables set up here, country coded to see if there were any differences in management technique, land cover, which was taken at the very broad scale. If you look at some of the other papers that our research group has published on, it is very difficult to get very fine scale resolution data of trying to delineate those savannas. It can be done because we've done it, but that's really difficult to do at a very large regional scale. So for the purposes of this paper, we use the Global Land Cover Facility data from the University of Maryland, which is one of the premier remote sensing centers in the US. They work with NASA a lot. So there are 28 different land cover types here. We use the majority rule. So whatever is the majority in that park, that is what that park was assigned. There are varying degrees of savanna. As I mentioned, right, it could be anything from pretty sparse grassland to pretty dense woodland. So all of these different types of savannas are accounted for in this land cover product. Then we have our area of our park or our buffer. This is in kilometers squared. And then we have our mean annual precipitation. So as I mentioned, we already know that precipitation is really important here. And so we went ahead and did this measure for MAP from the Global Historic Climate Network. We also have mean population density, because as I said, human pressures are really great on this landscape. Increases in human pressure would lead to more pressure on our protected areas. So we want to know how that affects it. Mean elevation, because we know that there can be a relationship between elevation and vegetation type. And then whether or not someplace was a transfrontier conservation area. So I pointed out to you, out of those 79 national parks, 31 of them were transfrontier conservation areas. So does that make a difference? And then our dependent variable, as I mentioned, was our mean seasonal by time period and DVI. Okay, it's a lot of big graphs here after this one. So we decided after testing for our 4 assumptions of linear regression to use a backward stepwise regression for this analysis. So this introduces the full model with all of the variables in it, and then it starts pulling variables out to see what the model performance looks like with or without those variables. And then after a certain time, it comes up with, this is the most reduced model with the highest accuracy, if you will. So in order to determine what the best models were, we use the lowest Akeki information criterion for model selection there. So here's all the big, big graphs. So here we're focused on the wet season. And we're focused on the wet season because this is when all of our rains are. So we wanted to know what was the relationship, particularly during the wet season when we have much more of the precipitation. So here we have parks and buffers laid out from across these time periods, the ones that I mentioned before, and this is in our December, January, February, so the first part of the wet season, and our March, April, May, and the second part of the wet season. So if we are, I know there's issues with R-square, but if we are looking at R-square values in a real world scenario, actually when we're getting in the 60s here, we're doing pretty well. But based on these Akaki's criterion, we can see that the models performed actually better in the parks than they did in the buffers. And this is showing variable importance. So if there's green, it means that it was a positive correlation. If it's in red, a negative correlation. And then the number of asterisks corresponds with the amount of significance. So land cover, for example, in the first part of the wet season, or December, January, February, wasn't very important across any of our time periods or study areas. Versus here in the second part of the wet season when land cover did become more important across all of them. This was a very expected result here, that with increasing precipitation, we were going to have increase in our NDVI. This was interesting here with our mean population density. We had more people obviously living in the buffer zones and in national parks where people are not allowed to live. So there was that negative impact there. But the two things I thought that were most interesting, I really thought that our size of park was going to be more important than it is. So when we got these results, I started looking at the literature and finding out why this might have been the case. And actually, it may be more about protected area remoteness rather than the actual size of the protected area. So that could be something, some sort of analysis to incorporate into this later. The other thing that I thought was very interesting was that when there was a transfrontier conservation area, there was healthier vegetation as determined through NDVI. So that was a very promising, what you want to see, correlation there. So after this NDVI, we went into a NDVI-based vegetation persistence analysis. So this is a pretty novel, very cool product that we originally came up with back in 2013 using advanced very high resolution data, which is now 8 kilometers, not so very high resolution. But at the time, back in the 80s, it was. So we went ahead and we have this persistence metric made. And this is really a neat product because you can tell interannual changes of NDVI in this at the pixel, spatially explicit manner. And this is based on a baseline period. So our baseline period, and in order to cover any sort of anomalies that might be happening with climate or anything else, it is a multi-year period. So in this case, we have 2000 to 2004 is our comparison period, what we're comparing to. Then after that, we have each of our 12 years later, 2005, 2016, comparing that back to the baseline. So what I mean by that, I like this graphic quite a lot. So each of those seasons, we're going to compare back to that baseline period. So if NDVI, if we're looking here in this bottom right-hand corner, if NDVI was a higher amount in one of those after years than it was in the baseline, then that pixel gets assigned a value of +1. If it was lower NDVI than that baseline period, it's assigned a -1. And then those values are accumulated over time. So in this particular case, we're talking about an N of 12. If every single year in 2005 to 2016 had a higher NDVI value than that baseline pixel, then it would be assigned a value of +12 for that pixel. And you would say, wow, there's been like a lot of positive. It's been consistently more positive than the baseline period. There is probably a trend going on there. Or the opposite, if it was every year was lower NDVI, then you would end up with a pixel value of -12. And you would say, ooh, there's probably some negative kind of trend going on there. Further exploration needed. So in this particular case, we're using, like I said, it's gonna be across the whole region. So we have values of + or -6 is for us deemed significant. So we're concerned with things that are either +6 or higher, -6 or lower. So this directional persistence, D, is that cumulative direction of change over time. So one thing that this does not account for is the magnitude of change. So we have another metric for that, but that only works where land cover data is very, very accurate, like it's been done here in Florida. But we don't have that data, as I mentioned, with the complications of remote sensing in savannas, and so that wasn't possible to do here at this time. So we have this directional persistence instead. So when we map out, right, by every single pixel across Southern Africa in December, January, February, or March, April, May, this is what we come up with. So areas that are very, very dark green, those are areas that were much more positive in NDVI than our baseline. Areas that are in dark purple, much more negative than our baseline. And then this, of course, is Lake Malawi, so disregard that, that's not vegetation. But one thing that a couple of things actually that I want to point out here is that in the beginning of the wet season in Western Southern Africa, we have a lot of really strong greening trend. And then in the second part of our dry season, we have this exact opposite trend in our Eastern Southern Africa, particularly in Mozambique, Zimbabwe, Botswana, and in South Africa. And you'll notice in particular that there is a lot of, I'm not going to call it browning, but less greening going on here where all of these countries meet. And so I would argue that this transfrontier conservation area is even more critical to try and combat what other larger climate drivers might be going on here in this system. And then, right, I should have pointed out large parks highlighted in blue, small parks highlighted in red, and medium parks highlighted in orange. So you can see that there's not an even spatial distribution across the whole study area. However, right, as researchers, there's nothing that I can do about that other than just analyze what is actually there. So then looking at differences again across season and then in our parks and our buffer zones, here we have our persistent percentage there on the y-axis, and we have our green being our positive persistence and this red, this burgundy, being negative persistence. So you can see that overall in our wet season, in our parks and buffers alike, which are both conservation zones, there is an overwhelming signal of green, right, of greening, of our positive persistence over time, with a much smaller amount of our negative persistence over time. A couple things to report here, though. We do see a difference with, this sounds confusing, higher percentages of positive persistence in parks, that should be like a tongue twister, rather than our buffer zones. And we also see higher negative persistence percents in our buffer zones than in our park. So our parks are still more buffered, represented, conserved on this landscape relative to our buffer zone. So of our model, our mean annual precipitation, population, and our transfrontier areas were the most important drivers. However, things that we might add in the future, as I said, if there was some index we could create of remoteness, or even if you just did distance to cities, that could be an important way to look at the remoteness and see if it's more related to that rather than size or connectivity. Period rainfall, rather than just having the mean rainfall. I mean, rainfall did perform very well, but we might get even more in detail if we use some sort of period rainfall. And burn area index might also be important because, as I said, fires were very important on this landscape. We saw that there was a dominant trend of positive persistence across these parks and buffer zones, although a little bit more, as I said, in the parks and in the buffer zones. But this does support our literature on global greening in general. Now, we're going to talk about a case study where that may not be the case. But at a regional scale, right, everything is about scale, talking about geography. At a regional scale, our global greening is supported here. So the hope is parks are functioning as designed. So for the second part of this, we're going to zoom into that park, Gorongosa National Park I mentioned in Mozambique. This is a really unique place because of its history. So it was originally Mozambique was the first place in Africa to be colonized by the Europeans, originally by Portuguese in the 1400s, so quite a bit before. And so here, as a protected area, this was actually created in 1920 as a hunting ground for the Portuguese. Then we have, in 1964, the start of a war for independence against Portugal. And so there's this war that starts raging after they become independent from Portugal, that now there's the question of who is going to be the ruling political party in Mozambique. So we have the Frelimo and the Renamo that then have this civil war that lasts into the 1990s. And there was still some conflict even after 1994. But the bulk of conflict is happening over this 30-year period, of which during 95 to 99% of all large mammals in this park were extirpated. So carnivores and herbivores alike. So this is a really interesting natural experiment because, right, I said herbivory was a really important driver. Now we just erase all the herbivores and then see what happens after that. So we have this establishment in 2004 of new management under governance that was a cooperation between the government of Mozambique and an American NGO. And the restocking efforts began in 2006 and have increased greatly since then. Most of you probably know this is E.O. Wilson. I had the pleasure of working with him out in the field. So this is his sort of last, what he's deemed to be his last great project before he dies. And he has established the E.O. Wilson Laboratory. So there's a lot of new science that's going on here in Gorongosa. This is an old picture. If anybody's interested, my very first introduction to remote sensing was my undergraduate honors thesis in Gorongosa National Park, looking at repeat photography over time. So this is one of the photographs I used because we have Mount Gorongosa in the background and also these structures. Here's Lion House. It was a lunch place that became flooded. This is on the floodplain. And I'll show you a picture at the end of lions use it now to hunt. They sit on top and look out over the plains to find game. So very interesting, unique situation that is now one of like the biggest conservation efforts in Africa. So this is another of the repeat photography I did from a plane looking. You can see here and there that we have a lot of bush encroachment over time. But how has precipitation, major driver in savannas, changed in the 21st century? What are the trends in vegetation abundance? And how do these trends in biomass on the ground relate to vegetation persistence? Are we seeing any kind of trend? So here's our study area. As I mentioned, we're here in central Mozambique. So study area is a little confusing. We have Lower Gorongosa highlighted here in purple, Mount Gorongosa highlighted here in black, our buffer zone 20K, which is in our teal. And then we also have further broken down into over here, the inset, you can see Lower Gorongosa. I have my open or grass dominated savanna class, our mixed, which is mix of woody and non-woody. And then on the eastern and western parts, we have our closed and dominated savanna. So here, here we go. So looking at precipitation, we had total annual precipitation that was accumulated from our monthly chirps, the same chirps data that we used before, that climate hazards group infrared precipitation with station. So it's a fusion between station data and remote sensing data at 0.5 degree. We had total seasonal precipitation, which was lagged 1 month, right? So our rains are coming first, and then we're seeing some kind of green up when we can best evaluate our vegetation health. So just for example, we would have February, March, April rain linked to March, April, May, and DVI. Then we went ahead and I wanted to see, right, remember I mentioned earlier about our pre-management versus post-management periods, and I wanted to see if there was any difference in our precipitation, kind of so we could just rule that out as one of the main drivers for any changes we're seeing. So we're using here our Bernoulli principles to determine, is it greater than we might expect? Are there more, is there more rain in a year than we might expect, or less rain than we might expect at random? So on this one, our zeros here are our means. So you can see this is by season. Our NDJ, 550, 384, 80, and 61, right? So our wet season and dry season images here. And then we have Anything that's in blue was above what the mean, and anything in red was below that. However, when we looked at that over time, we didn't really see that any of the years were higher or lower than we might expect at random. So we did not have any strong trends there. However, when we start here looking at our different seasons by themselves in terms of our change over time, we can see that in particular in our February, March, April, and May, June, July, that we do have a significant decreasing trend. And we put this all together for our seasonal totals over time, and we look at what are our anomalies here, what are our standardized scores, apart from that mean, that there is a decrease, a significant decrease in precipitation over time, but you just can't tell it between our pre and post management types. Then here we're looking at our seasonal NDVI by period. So here's our seasons, here are our periods. Again, we have our lower Gorongosa, our buffer, and our Mount Gorongosa. And I will note, many of you are probably wondering about this little dot here in the middle. That is Lake Urema. So that is a permanent lake, but of course it expands and contracts depending on the season. But that whole area has been excluded from the analysis so as not to negatively skew our NDVI values. So a few things to point out. You can see that in general, across all seasons, towards the center of the park, we have lower NDVI values than we have going out to the east and west. And again, that's related to our vegetation type. So our grasses are going to have lower NDVI than, say, our woodlands that are bordering there. And then you can tell seasonality in here as well, that we have the highest of the high NDVI values in our March, April, May, the second half of our wet season. And then we have the lowest of the low NDVI values in the second half of that dry season. So looking a little bit closer at NDVI, these graphs with our values and our anomalies were done for all 6 of our study types, study areas. However, the only ones that were significant were our Mount Gorongosa and our open. Mount Gorongosa is really unique. You did see it was separated physically from the park. It's anything above 700 meters on that mountain. And it is really unique because rather than being a savanna, that is actually a montane rainforest. So less variability in terms of NDVI over the year because, right, it is a rainforest rather than a dryland. But also it's more vulnerable because there's a lot more human pressure that's occurring around that part of the landscape. And then we have here our open savanna, which is our grassland dominated savanna that had the highest or the largest amount of decline over this time period. And again, we know that our grasses are more vulnerable because of their root system and their response to rain than some of our more established trees. So our closed, there was no real trend in our woodlands over time. And our inside park, the whole of the park versus the buffer also looked quite similar, although the park fared a little bit better. But I just wanted to mainly highlight this so you could see where the biggest decrease trends were. And then examining our NDVI here a little bit more closely. Here in this first figure, this is 2000 to 2004, and this is daily NDVI data here from our MODIS in days since March 1st, so going through the year. Here in our dry season, actually, we have much higher NDVI values. We have much greener than we might expect here on the long-term mean. And then also during this period, during our wet season here in our March, April, May, December, January, February, we have much lower, less green. Here, 2005 to 8, most of the year, we have this negative anomaly compared to the longer term mean from the second half of the dry season all the way through the beginning of the wet season. Here, 2009 to 12, we have higher than we might expect in both parts of the wet season, in the beginning and the end. Not as many anomalies happening here in the dry season. And then in the most recent period, our 13 to 16, we have that positive anomaly happening here in the second half of the wet season rather, and into the first half of the dry season. So to break that down for you a little bit further, over here in the top right, and again, this is related to, this is the first time period, second time period, third time period, fourth time period. Sorry, it's not written on there. But you can see negative versus positive anomalies. They're in terms of magnitude, which is here on our y-axis. They're relatively even, except for in this second period, our 05 to 08, which corresponds with this overwhelming trend here of negative anomalies. And then the last thing that I want to point out here in the bottom right-hand corner is about timing of NDVI. So this top part of the graph symbolizes the uppermost 10% of NDVI across the study area, and the bottom half of the graph is the lowermost 10% of NDVI across the time study area, and each of these is a separate time period. So things that are important to note here are that green up in the earlier part of this time series was happening much earlier than in this later part. So in other words, our green up is happening this much later. So in some cases, almost 50 days later. And so that could be significant because there might be some changing of rains. But one other thing to notice when we look at the structure here is there's a lot more variability in when our maximum green up happens in the earlier part of the time series, whereas it is more consistent here in the second half of our time series. And then when we compare our lowest 10% of NDVI, it is relatively less variable over time, both within time period and across time periods. Although we have seen here that we have, especially as we get towards the more recent period, that we have our browner, less green happening even later into the dry season. So could be that rains are coming later there. And then here we have looking at our precipitation versus NDVI. Again, these are by our periods and our seasons. So we have here, all four of these have a significant relationship with our precipitation. But when we look at them all together here on this graph, you can see that there's much steeper gradient here during our dry season. So this is in the beginning of the dry season and the end of the dry season. And this could just be because anytime that you have lower precipitation, if there is any precipitation event, vegetation is going to be much more sensitive to that increase in precipitation than, say, if we're already into the wet season and precipitation is regularly occurring. So in terms of our directional persistence for this landscape, again, the same lower Gorongosa buffer and Mount Gorongosa, the same that you saw before, where areas of dark green were a greening trend, areas of dark purple were a not greening trend. I don't call it a browning trend, but a not greening trend. So particularly here in our dry season, our June, July, August, September, October, November, there's an overwhelming amount of purple on this landscape. So especially in our buffer zone, but also sadly, and even in the wet season, you can see on our mountain. So taking these maps and breaking them into numbers here, here's our mean seasonal directional persistence. So this would be the actual value of our persistence. So in our dry season here, we have our mean value of directional persistence being quite negative across all of our study areas. So this is lower Gorongosa, buffer, Mount Gorongosa, open savanna, mixed savanna, closed savanna. So across all of those in the dry season, we have this negative mean. And then during the wet season, we still have that high negative number in Mount Gorongosa and barely a positive number in our open, which makes sense because those are our two most vulnerable landscapes. The ones who did well were our mixed and our closed, so our woody vegetation. And then further breaking this down into percent of landscape that is either positive or negative persistence dominated. And then here we have our seasons, December, January, February, March, April, May, so on and so forth, across our same 6 study areas. What we can see here is that in our wet season, we do have more of the landscape that is positive, significantly positive, but there's still also quite a bit of significant negative. Then in the dry season, and remember when we're looking at the dry season here, everything looks quite purple. You can see that the majority of the landscape across these study areas and season months is overwhelmingly negative. In some cases here with our open savanna, up to 75% of the landscape is significantly negative. So just to firm up about our vegetation persistence, it is very different than some of our traditional conversion approaches to landscape change in remote sensing, because we can look at those areas of vulnerability at the actual pixel level and determine some sort of trend there. So we did look at that pre-post management precipitation and found that it was not significant. But when we look at the time series as a whole, there was that significant decrease over time. Also, our NDVI trends were all negative over time, but they were the steepest, and the only places that had significant decline were Mount Gorongosa and in our open grassland savanna. So vegetation type really does matter. It does matter that we're out here trying to delineate these different vegetation types. One thing about this is that it actually, this specific park, right, in the last paper we were just talking about all parks, we said it is appearing to have a greening trend. Now when we zoom into this one park, it actually supports browning hotspots in sub-equatorial Africa. So this does link in with that literature that scale really does matter at what level you're looking at these things as well. One thing that is really interesting about here, though, part of the conservation project that they're doing is they are planting they're planting coffee at the rainforest on the mountain. And one of the ways that they're doing that is with all the coffee that they're growing, they're also replanting that native rainforest. And so with that, let's see, so they've got several thousand hectares already of rainforest that they have restored. So that is looking up, that's changing now in the last few years, and hopefully will continue to be positive. The other thing here, we're talking about bush encroachment. So because of this absence of herbivores, my first study that I did, I found that large trees were able to grow and persist here, unlike a lot of other places in Southern Africa where you see the movement away from those large trees into more bush encroachment. But one issue they had in Gorongosa on these vulnerable open grassland savannas was Mimosa pigra that was encroaching. Now that they've seen all this restocking of animals, they've had research that's come out this year that said actually now they're seeing, because of the animal populations coming back, a decrease in that bush encroachment of Mimosa pigra. So that's pretty cool, but obviously, right, we're talking about herbivory having an impact on the landscape. We have to be careful about how many animals we bring back as well. So they're trying to get back to their 1970s baseline is what they're working with. So we did see as a whole, though, that Lower Gorongosa as a whole park is doing better than the buffer zones where activity is happening surrounding that. So we definitely need protected areas. So these studies are just to improve remote sensing of savannas, understanding those vegetation dynamics, potential degradation, and hopefully something useful for managers as well. A little bit about more current work. One thing about Gorongosa that we're working on right now, something I was really interested in, it's a model called Savannah, all capitals. It's a crazy, complicated model that I'm working with some engineers on, so I'm not doing that actual part. But I wanted to see, can we determine what would have happened if we didn't have that loss of herbivory? So it's kind of cool because we can actually test, we did see that loss. Can we use this model to get the results that we actually have in reality? And then if we tweak it, what could have happened? If we'd had increasing in animals, if we had animals staying the same population, what would have happened? And now with restocking, what is going to happen in the future? So that's one project. And then a little bit closer to home here in Florida, there is some of you may have heard of the Indian River Lagoon. It's a very long, thin, here's the entire study area, in the east coast of Florida, Space Coast. And this is a marine protected area. However, because of algal blooms and increasing, similar to African grasslands, increasing herbivory with manatee densities, we have seen this drastic decrease in seagrass over the last 10 years. So I'm currently working on mapping the seagrass extent. This is part of that NASA proposal for young investigators we're talking about, and also seeking how does that change biodiversity and socioeconomics of people who depend on this lagoon. So there's, I think it's estimated that for every hectare of seagrass, it supports 100 million vertebrates and $10,000 of economic activity per year. So this really does matter. And then it also plays a very important component in the carbon cycle. But I just like this because this is that coarse relatively coarse, 30-meter spatial resolution from Landsat. And you can see here, clear as day, in July 2013, where the seagrass extent is. You can see it all. And then when we look now, when we know, and based on field excursions, that the seagrass is almost all gone, you can definitely see that drastic change. And then here is what it is now superimposed with our historic seagrass extent taken from the FWC. But yeah, even in this completely zoomed out image, you can really see where all the seagrass loss has occurred. So that is my next project here, along with a few other things in Southern Africa, but because of COVID, who knows? And this was the lion house that I was talking about in Gorongosa. And there's my email if anybody wants to reach out to me. But thank you all for listening today. I really appreciate it. And I think they're taking care of questions. So if you have questions, I'll check the chat box.
So by far the weirdest part of these things is the silence that occurs when you get done speaking. So I'm going to unmute everyone and we're all going to give a big applause. Ready? 1, 2, 3.
Thank you. Thank you. Okay, unmuted. I guess I will just read through the questions here on the right-hand side then. Eric Carr says, you mentioned you could not select where your parks are located. Have you considered doing the analysis with random regions for size and location designated at parks, excluding urban? No, I had not considered doing that analysis. The next sort of step that I had been thinking of was looking at distance from those urban areas. Amanda, for these greening trends in the national park, are there ways to tell if greening is caused by native or invasive species? That's a really, really important distinction. Thank you for bringing that up, Amanda. You can't tell from this scale is the answer. So some of the work that I've done, such as in Chobe National Park, actually looked and said, oh, we do see this greening trend in NDVI over time. But actually then when I went there to do field work, they were evergreen shrubs that aren't invasive, but they're low grade pioneer species that really nobody can use. They come in, they take over the landscape, and they're just not very helpful for biodiversity or for supporting animal populations that we need for tourism numbers or anything else. So that is definitely why, and hopefully I've highlighted that smaller spatial scale studies here are also neat for sure. Focus mostly on the health of vegetation, but does your research look at how vegetation biodiversity is affected by transfrontier parks, precipitation, et cetera, in these parks? I have not looked at biodiversity. Biodiversity measured from remote sensing is not what I would consider to be the most accurate. Yes, there are some global biodiversity products out there. The UN has one on their biodiversity lab website, and those are okay, but it's more important to actually go there and determine what the biodiversity of those landscapes are. So that would need to be a more detailed study in a lot of different places, which is why everybody's small scale work is really important too. Oh, what do I like most about field work? I don't know, when you get up in the morning with a cup of coffee and go look at some lions roaring, maybe eating some dead things, that's pretty special. Yeah, definitely my field work is really cool because we get to like drive around through all the parks, so we get to see lots of wildlife. That would have to be my favorite. What led you to study this field? That's an interesting question. So in high school, 7 other ladies from the barn and I went and did a riding safari across southern Kenya. That was about 300 kilometers. And I absolutely fell in love with the landscape. And at that time, right, it was high school. I thought maybe I would be a vet or something. I didn't know. But when I went there, I was like, okay, I have to figure out how to work in Africa again. So when I got to my undergrad at UF, I applied for a National Geographic internship and got it, and met some people that were working on that project in Gorongosa National Park. And they came in and said, oh, we want you to do this repeat photography project. I said, okay, sounds great. I don't know anything about remote sensing. And so I learned that, and I thought it was really cool. When I came back, my advisor said, okay, now you're doing a master's, you have to learn about satellite imagery analysis. And I was quite resistant to it at first, but it's really worked out. And I do like that you can really scale things up using satellite imagery. Let's see, thinking about linking biodiversity to greening trends, is there a feasible pathway modeling-wise for linking wildlife conservation outcomes to the greening trends that you've examined in this work? Sure. So do you mean like understanding different management techniques in different places and how that has changed these greening trends? So things more like looking at herbivore numbers or if people are burning or not burning? Nathaniel? Oh, okay. Well, if that's what you mean, then yes, that's some of the work that we're going to start doing with this savanna landscape, is that what major wildlife. So things like, you know, lions and elephants, all the big players on the landscape, the environmental engineers, if you will, those in terms of biodiversity will be linked to these trends on the landscape. Thank you, Amber. I appreciate that. Let's see, you focus on national parks. Is there variation across Southern African countries and other types of protected areas that could be important for savanna persistence? Certainly. There's definitely a lot more work to be done, especially in privately owned conservation areas, because they do things so differently, because they don't have to follow all the same rules and regulations as a national park. So I would imagine that that definitely has an express difference. That was just when you go up, right? So there's like 79 national parks. When you go up to all of the different types of protected areas, now we're talking about thousands. So that would be something definitely to look at in the future. Are there any members of the wildlife, be it beetles or elephants, that contribute in any very significant way to preservation? Yes, definitely. Michael, you remembered from class. So everybody, I start to get myself into a little bit of trouble with this. So everybody, of course, hears about how endangered elephants are and how elephant poaching is occurring every single day. And that is all really, really true. But the thing that I like to focus on there is that it also depends on the region that we're talking about. So in Eastern Africa, that's like 100% true. Numbers are definitely declining. They're not having a lot of impact on the landscape. But when we transition more into Southern Africa, there are some places, not Gorongosa National Park, for example, right? But places like Chobe National Park in the Okavango Delta that actually have too many elephants. So that's where things start to get tricky, because what do you do about that? It's very difficult to transport elephants. No one likes to cull elephants. Hunting in a lot of places is banned. So that is definitely tricky, but elephants absolutely can destroy a landscape without a lot of effort. Lots of debarking, ringing of trees, and knocking trees over, and then allowing the pathway for bush encroachment to happen. And then hopefully some kind of fire or something comes and puts the competition back in the other direction. But these savannas are constantly cycling through different levels of woody versus non-woody vegetation. How would you say economics and politics play into the conditions of national parks? Oh, absolutely. Everything here. Management is extremely important on this landscape. And that is one thing that I really hope to incorporate more of in the future, because everything is about politics. So for example, in Eswatini and in Swaziland, the king might just decide that he's going hunting today in this park, and so now the whole park is closed, or he doesn't want fire to be burned. And then on the other hand, you could have somebody who's working with a lot of environmental groups, maybe like in South Africa, where they want management done a completely different way. And then there's also a lot of corruption or conflict with, can we make community-based natural resource management work? If people are actually, you know, actors having power on the landscape, they're contributing to this conservation. Hopefully they're also getting something back out of it, but not always. If politics aren't right, if governance isn't right, if there's corruption, even at the chiefdom level, then that can all be skewed, and people end up, right, in a situation where they may need to do things like hunt for bushmeat. So definitely really, really important. Thank you, Latoya. With regard to the Space Coast, what is your intuition about human power plant boat truck? Yep. So for that project, the number one problem here are these algae blooms. Now, algae blooms of certain species were quite regular here over time. Then something happened that's never happened before. There is a species of algae that had only previously been seen in Texas and had devastated lagoons in Texas during this century. Then the second half here in the 2010s, it somehow magically appeared here. Now, we don't know why that's happened, if there was some natural migration. There's also a lot of people that are going between those exact same lagoons in Texas and lagoons here. There's also a lot of oyster transfer. We're not sure why, no idea, so I'm not placing any sort of thoughts on that, but those are different. These algal blooms are much more severe in outcompeting our seagrasses. So that's definitely, and one thing that allowed them to colonize here so quickly is we had really cold snaps in 2010 and 2011, and that gave the opportunity for these algae to bloom up. But that's the number one thing. Then, of course, there are other implications. So you're talking about boat traffic, right? Boat scarring of seagrass meadows. Most of what's happened here during, again, this century is a pole and troll zone is now in Mosquito Lagoon. So you can't just go whipping through there with your boat. You have to be poling your boat or using your trolling motor. So I think that is less so now in this current time period of degradation that we're talking about there. But one thing for sure, of course, pollution, right? Pollution was the reason, those nutrient inputs for those original algae blooms, not the new one, but for the original ones. So it's interesting because those previous algae blooms were more linked to that nutrient input. The newer ones are linked to more climate and those cold snaps. So I think it really depends. Obviously, seagrasses are important for buffering against hurricanes and large storm events, but there's not a lot of science, and certainly not here, that's been done on what effect that really has on seagrass extent. Temperature, increasing temperature can definitely lead to seagrass die-off as well, which we have seen here the last few years. So it's kind of a perfect storm of bad things. And then finally, yes, so the southern end of Mosquito Lagoon, which it's right out my window, is the NASA launch pad. I watched a rocket launch this morning. And so at that launch pad, there's a lot of toxic chemicals, fire retardants in particular, that they're currently working on evaluating and cleaning up. No idea what the effects of that is yet. And then there's also warm water power plants, which unnaturally attract all the manatees. So Florida has about 7,500 manatees right now. So that population has recovered, but about half are on the east coast of Florida, and about half of that are currently aggregated right out here because of those warm water plants. So they're able to survive here throughout the winter very comfortably. So people have proposed trying to almost set like a fence, a barrier, to try and move the manatees back, just to make them uncomfortable enough to move back south where the population can be a little bit more evenly distributed. But that definitely has an impact because they can eat up to 100 pounds of seagrass a day, right? And we're talking about 2,000 animals out there. That's a lot. So again, I get into trouble with that one too, though, because I love manatees. Manatees and elephants are my two favorite animals, actually, but they're definitely engineers. Are there any wildlife interacting symbiotically in big ways? Not sure what you mean by that exactly. Oxpeckers pick ticks off of buffaloes? I'm not sure what you mean by that question. Maybe you could specify a little bit more. What might be causing these new, more severe algal blooms to appear? Yeah. So that is the question that we're still trying to investigate. But there have been papers already that have linked those cold snaps to allowing that algae to bloom here more severely, but still under investigation. Hopefully I'll help answer some of those things. Any other questions?
Great, thank you, Hannah. And thanks everyone for the questions. If there's any other questions, I'm sure that you can send them straight to Hannah. She'll be happy to answer them.
Yep, happy to chat. Thank you so much for having me. This was really fun.
Yes.
It's great to meet everyone.
A couple of things I wanted to point out to everyone while you're here. If you liked what you saw today, we actually run a interdisciplinary graduate student reading group in conjunction with this seminar series. So if you're interested in, if you're a graduate student, you're interested in participating, or you are faculty and you have a graduate student that you think would benefit from these types of discussions, reach out to Paul Armsworth, and he will be leading the group this semester. You can reach out to me, either one, and I can put you in contact. But the idea is that we sit down every week and we read a paper and discuss it. And so it's sort of like a small version of this in a more intimate setting with a handful of graduate students. And that's a one credit hour course that's run online this semester. Paul's got his email address there in the chat box if anyone's interested. I also want to remind everyone, September 7th, if you're interested in climate change work, we'll have Andrew Hoffman here from Michigan, so put that on your calendar. Lots of interesting things about how culture and climate change interact to influence that discussion. Finally, I want to say thanks to Elizabeth Woody at the Baker Center for putting this all together. These things are not easy to do, making sure that everything works and you can hear people and you can not hear people and what have you. So thank you to her for putting this together. If you have any recommendations for how we could improve this, you can email me or you can email Elizabeth, and we'll try to incorporate those to try to make this work as well as it possibly could in its online fashion. But with that, I will call it to a close. Thank you, everybody.